Hey kids, so no, apparently there's some glitch going on with my Screencastify. So hopefully I can get around it by doing this. All right, from the beginning. So as Clarissa called this, my backstory about Melrose Games and my grandfather's awful taste in food. Because anyway, the point here was that when you get a box of Cracker Jack, and I gave you all tattoos, which was a great idea, that it would take about 5 boxes of Cracker Jack before you got one tattoo. And so you get these 4 crappy stickers and one tattoo every 5 boxes of Cracker Jack. And I asked you stuff like how many boxes did you have to get 3 tattoos? And how many stickers did you get for 3 tattoos? And you figured this out really quickly in your head. And that's because you're using this balanced equation. You have these numbers and you just put them together and you can figure that out. And what we're doing now, stoichiometry, defined as, oh, kids, my head hurts a lot. Stoichiometry, there it is. All right, stoichiometry defined as calculations involved in a chemical reaction, so you can figure out specific quantities. The first thing we talked about was the idea of a limiting reagent. That is, I don't know why this is going without me. Woo-hoo. Thanks, everybody. All right, so gremlins. So if you have 2 starting materials, like if you're making Oreos and you're trying to figure out how many Oreos you can make, and you know the balanced equation is 2 wafers have 3 grams of cream in between them to make 1 Oreo, then you should be able to figure out, here we go, you have 20, oh my lord, you have 27 wafers and you have 27 grams of cream. You can figure out how many Oreos you can make. And in fact, you don't even need to do math because you'll probably very quickly realize that 27 wafers, because there's 2 wafers in an Oreo, will give you 13.5, or basically 13 Oreos, because you can't really have half an Oreo. And the 27 grams of cream, because there's 3 grams of cream in one Oreo, will give you 9 Oreos. So even though you have enough wafers for 13 Oreos, the answer is 9, because even though you have enough wafers for 13 Oreos, it's not an Oreo if there's no cream inside, and you won't have enough cream to make 13 Oreos. So we call this the limiting reactant, and I'll call it reagent sometime. Just forgive me. So that's what we called it in the big business. All right. So that limits how many you make because it gets all used up in the process of making your product. So first thing we need when we do stoichiometry is a balanced equation. So balancing this equation here, you look at your oxygens first. You have a 2 and a 3. And since the least common factor for those is 6, that means you need 2 of these and 3 of those. And that'll give you 6 oxygens here and 6 oxygens there. But in the process of that, you've now made 4 aluminum. So the other thing you need to do with these equations in this unit is look at a problem and figure out what it's asking for and what you have already. So how many is always a good indicator, how many moles of aluminum for what you're looking for. So what is needed here, if your boss sent you this email, is moles of aluminum. He won't leave you alone until you tell him how many moles of aluminum you got. Now, when you see a number, that's a good indicator of a given. So 3 moles of oxygen, we have 3 moles of oxygen. So you start with your given, 3 moles of oxygen, and you go to what you're needing, which is moles of aluminum. And you remember from our dimensional analysis that you can cancel moles of oxygen by putting it in the denominator, and that'll cancel these out. And you want to go to moles of aluminum. Now, the place where you will find this relationship between moles of aluminum and moles of oxygen is this balanced equation. So the number associated with the oxygen is a 3. So we'll put a 3 there, and the number associated with aluminum is a 4. So we'll put a 4 there. And 4 times 3 is 12, divided by 3 is back to 4, so that will give you 4 moles of aluminum. You could also just look there and see that, yeah, if I have 3 moles of oxygen, I need 4 moles of aluminum. All right, that's easy for that one. It gets a little more complicated when the numbers get more difficult. So here We have the same equation, aluminum and oxygen making aluminum oxide, but this time it's asking how many moles of aluminum. So we still need moles of aluminum. Thank you, computer. Moles of aluminum. And our given, here's the number that's going to help us, 5 moles of aluminum oxide. So we're given 5 moles of aluminum oxide. So we're trying to make the aluminum oxide, and we need to know how many moles to go get out of the cupboard to do this. So our given will start here, 5 moles of aluminum oxide. That's what we need to make. And the question is, when we go back into the lab, how many moles of aluminum do we need to pull out? So we're going to cancel aluminum oxide on the bottom, and we want moles of aluminum on top. And we get the relationship between these two in the mole-to-mole ratio from the balanced equation. So that tells us that there are 2 moles of aluminum oxide for every 4 moles of aluminum. 5 divided by 2 times 4 is 10 moles of aluminum would do it. All right, so here we go with something more difficult. I've already started to write this. So when aluminum reacts to make aluminum oxide, how many moles, here's the word, how many moles of aluminum, so we need moles of aluminum again, 8.5, that's a good given start. That's a good given start. Moles of oxygen, so we want moles of O2 here. So we're going to start with the 8.5 moles of oxygen, and we're going to go to moles of aluminum. And we do that by first canceling the moles of oxygen, going to the moles of aluminum, and we get that relationship from the balanced equation. Oxygen has associated with it a 3, and aluminum a 4. So 8.5 times 4 divided by 3 is, there it is, 11.3 moles of aluminum. But since we had 2 significant figures here, we want 2 significant figures there, so that would be the same as 11 moles of aluminum. Now, I'm not going to crush you for that right now. I just want to bring it up because it is still important that how accurately you measure something will determine how accurate your answer is. And these numbers here in the from the balanced equation are infinite significant figures. That is exactly 4 moles or 4 atoms of aluminum that reacts with exactly 3 atoms or 3 moles of oxygen. So they will not determine your significant figures. All right, here's another one. Given, here's our number. So that's a good point to start with a given, 6.50. And I know that's going to annoy many of you, so I'll erase it. There you go. You're welcome. So 6.50 moles of aluminum. So that's the given. And we need how many moles of aluminum oxide? So we need to get 2 moles of aluminum oxide. So we start with 6.50 moles of aluminum, and we go to moles of aluminum oxide. And to get there, we will need to cancel moles of aluminum. And we get this mole-to-mole relationship from the balanced equation. Here's moles of aluminum, and here's moles of aluminum oxide. So it's a 4-to-2 thing. And 6.5 times 2 divided by 4 is 3.25. And that's how many moles of aluminum oxide we would make. And that's accurate to significant digits. That's 3 and 3. All right. So example 4, now we have a whole new reaction. This is a propane reaction, but you're still going to do the same thing. You're going to look through the reaction, and if you're not sure what propane is, it tells you propane gas reacts with oxygen. So propane reacts with oxygen. If you didn't know that was propane, hopefully you knew the other one was oxygen. So how many moles of water are needed? Moles of water. Moles of water is this one. And 6.7, there's a number to tell us it's moles of propane. So 6.7 moles of C3H8 is the given. So we're going to start with the 6.7 moles of propane. There you go. And we want to get to moles of water. And we're going to do that by canceling moles of propane. And we're going to get the relationship mole to mole from the balanced equation. So balanced equation for propane shows no number, so that's understood 1 because we wouldn't have drawn the whole formula for propane if we didn't at least have 1. And for water, that's a 4. So 6.7 times 4 divided by 1 equals 30.1 moles of water. which is good with significant figures. That's 3. So 30.1 moles of water. All right, how many moles of carbon dioxide will form with 2.14 moles of oxygen react with excess propane? So again, here's your propane. That's excess, so that means we have all the propane we need. So that is not anything we need to worry about right now. It's asking for moles of carbon dioxide, so we need moles of CO2. And here's a number to tell us who our given is. 2.14 moles of oxygen gas, so 2.14 moles of O2. So we're going to start with the 2.14 moles of O2, and we're going to go to moles of CO2. And in order to do that, we're going to have to cancel moles of O2, and this relationship comes from the balanced equation. So there's a 5 associated with the oxygen, and there's a 3 associated with the carbon dioxide. So 2.14 times 3 divided by 5 is 1.28 moles of CO2. All right, last one. So this is what we call a limiting reactant problem. So how many moles of carbon dioxide is what we're needing? How many moles of carbon dioxide? And since we're given two numbers, 10 moles of propane and 10 moles of oxygen, two numbers given, that's how you know it's a limiting reactant problem. So I'm going to write that in a different color so you know that's a limiting reactant problem. Has two givens, right? Because it's basically saying I have this many slices of bread and this many slices of cheese, and how many products are we going to make? Now, this one specifically asks for a product. It's asking for carbon dioxide. But if it was just asking for how many, which is the limiting reactant, you can just go to any product, right? If we were making Oreos, we go to Oreos. If we're making cars, we go to cars. In this case, we have a choice of two products, so we just have to choose one. Since the question asked us for moles of carbon dioxide, that's what we'll go. So the two givens are, one is the 10 moles of the one reactant, C3H8. So we'll figure out how that'll go to carbon dioxide. So moles of C3H8 will go on the bottom, and moles of CO2 will go on the top, and we get this mole to mole ratio from the balanced equation. So the CO2 has a 3, and the propane has an understood 1. So that means 30 moles of CO2 will come from the propane. And then we do the exact same thing because we had two givens, 10 moles of oxygen, and we figure out how much carbon dioxide that'll make. So we need moles of oxygen on the bottom, moles of CO2 on the top. The relationship there is there's a 5 associated with the oxygen and a 3 associated with the carbon dioxide. 30 divided by 5 is 6 moles of CO2. So you learn, because this can only make 6, that one can make 30, that this is the lower amount. So even though we have enough propane to make 30, we only have enough oxygen to make 6. So we say oxygen is the limiting reactant. And that's what that means. So I think that's it. We'll get into this in a second. I hope this worked. Have a good day.